So let's get started, everyone. So welcome back. So today we'll be talking about total probability. We're we're pretty close to finishing up the basic probability section. But let's start by just so kind of going through this. So kind of brain teaser. I don't know if this is teasing quite as much as some of the other things we'll do, but we'll kind of start by going up on this interesting example that I put up at the end of the last lecture. So the problem was we have one urn and it's got 4 balls in it, right? And the 4 balls have these different labels. 110, 101, 011, and 000, right? And you have 3 types of events: A1, A2, and A3. And AK indicates that there's a 1 in the kth location. All right, and so you can work out that the probability of each of the events, so A1, A2, or A3, is going to be 1/2. Right, exactly 1/2 of the balls have 1 in each of the positions, right? And if you look at the intersection of A1 and A2, so the set, let's make the font smaller. If you look at intersection of A1 and A2, this is only going to be exactly one. Example. Right, so we have the probability of any event AK is going to be equal to 1/2. We also have that the intersection of each A1 and A2 is for any 1 and 2 or 2 and 3 or 1 and 3, that will have the probability that A1 intersection A2. This is also this is going to be 1/4. That means that the probability of A1 times the probability of A2 is going to be 1/4, right? That's 1/2 times 1/2. 1/4, and so they're going to be independent of each other, right? A1 and A2 are going to be independent of each other because the product of A1 and A2 is equal to the probability of A1 and A2 being true at the same time. If I go through the same example, the same exercise for A2 and A3 or A1 and A3, I get the same thing. But if I look at this question now, this third question here, is the event A1 intersection A2 independent of A3? Okay, so now I say so I can do, if I want to know, I can look at this in this way. If this is true, then I should have that the probability of, let's say, A3 is equal to the probability of A3 restricted to A1 intersection A2. So let's do it the other way around. Let's say probability A1 intersection A2, is that equal to the probability of A1 intersection A2, given that A3 is true, right? So they're going to be independent if that blue equation holds, right? So does this blue equation hold? We know that this is 1/4. Probability of A1 and A2 is 1/4. But if I restrict to A3, I'm going to have these 2 balls here, 101 and 001. Okay, so that's my restricted sample space, given that A3 is true, but none of those are in A1 and A2. Right, so this side is equal to 0. So these are not equal to each other, and these are not independent. Okay, so even though there are three pairwise independents, I don't have a kind of a three-way independence between these sort of sets, right? So this is kind of a tricky concept. Just because pairs of events are independent doesn't mean that all kind of that all combinations of the events are independent. You can still can still give rise to these sort of situations. So okay, so this is more of just something to kind of keep in mind, that independence is not like transferable through like intersection and stuff like that. You should actually so work these details out. So okay, great, good. Any questions on this? Or all right, so let's look at the web page where we are in the class. Homework 1 was due at the end of the day on Tuesday. Did everyone? It looked like we mostly resolved all the issues with turning in homework 1. I've heard from a number of people that the process of printing stuff can be a challenge. I have, I'll mention shortly, homework 2 is out now, and I'll show this, and there are printed copies of homework 2 up here. I'll try and bring a number. I'll try and figure out roughly what the right number is. So if you actually come to class, then you can get a printed out version. Hopefully that makes the upload process through Gradescope, not too onerous. You can take pictures with your phone if you have a camera phone, for instance, to kind of get stuff to upload as well. So hopefully that's not too hard. Does anyone have any like special challenges that they think there could be a way to improve it? But otherwise, all right, we'll see how the first grading goes, but I hopefully this will all go so smoothly. So homework 1, we'll try and have that graded by the end of next week. That's the target sort of schedule here. So we'll see how that goes. Sometimes the first one is a little different as we get everything kind of in place. Okay, quiz number 2 is also happening today. Okay, so you've taken 2 quizzes already. These are going to be on Canvas and a class. So I'll stop class, a little bit early on Thursday to give time for the quiz. Yeah, so as I mentioned the last class, this quiz is not going to be just multiple choice. So if you're doing it on your phone, there'll be a chance to type something. Again, like the first few quizzes, I think the average score was quite high. A few silly mistakes that hopefully will even out over the semester. So I hope this one is also easy if you're following along with everything in the class. So okay, and then like I said, yeah. So we have lecture today, and then Bayes' rule, which will be on Tuesday next week. This will wrap up kind of the basic notions of probability. After that, we'll get into a concept called random variables and how they interact first with discrete distributions, then with continuous distributions. A lot of how you interact with probability in kind of modeling things is through the notion of random variables, and this is kind of a complicated topic, and so it's going to be kind of something beyond events. And so we'll spend some time looking through a number of examples with those, with discrete distributions and then continuous distributions, and how we can kind of measure things on properties of random variables. Okay, so homework 2 is out. It's always linked off of here. It should also be linked off of Canvas. So it's in the column where it says out. And it's not on Gradescope yet. We still need to encode it on Gradescope. That'll be done by next week, Tuesday. So you have a whole week to upload it. But it should be fairly similar to the structure of homework 1. Again, you're asked to kind of write on the page and make sure you upload all 5 of the pages. And if you have extra work outside the space, I hope we've given enough space for your work on there. But if you need extra space, put this at the end. Yeah, and so okay, that'll be due in about a week and a half. All right, but we should cover the first homework. Maybe we kind of, you were learning some of the material up until when it's due. This one should cover up through, so Bayes rule. So you should be able to see Bayes rule and then still have a week to finish all the stuff on the homework. And I think now that we're into the semester, it should be, closer to this pattern going forward. So, okay, great. All right, before we get started, I wanted to do one more brain teaser to think about, and we'll see if we solve it or we just leave it for you to think about. So who's heard of Let's Make a Deal and Monty Hall? All right, so a few people. This was even before my time, so I'm not that old. But I think it was, when was this? Like in maybe the 60s. There was a game show on TV where Monty Hall was the host, and there was a common thing where he would have 3 doors, and a contestant would get to choose and keep whatever is behind one of the doors that they chose. And so usually there was a car behind one of the doors, and the other 2 doors had goats behind them. I think you could actually, sell a goat for non-trivial money, but most people didn't want the goats. They wanted the car, right? So your goal is to try and get the car. And so you don't know where it is. So you choose one of the doors, A, B, or C. After that, the contestant would choose, so the contestant choose one of the doors, but does not open the door yet. Then, so Monty Hall, he would know where the car was. So he would then take one of the doors that the contestant did not choose, and choose the one that they did not choose that had the goat behind it, and open up that door and say, well, this other door, good, you didn't pick this other door. There's a goat behind this door. There's always one goat that was not, at least one goat that wasn't chosen, that he can open that door. And then he says, well, you can now switch to the other door if you want to, right? So if you happen to choose A first, and he opens the one with the goat behind it, which might be B, then say, the contestant, you can switch to door C if you want to. All right. So is it beneficial to switch to door C? And if so, what's the what's the probability going on? Yeah.
It is beneficial to switch most of the time, and ends up being I think that from switching after the unchosen undefined.
Yeah. So there's one student is saying that if you switch, you get a 2/3 chance of getting the car. That's the claim. Yeah. Yeah. So there's one person saying that there's a 2/3 chance. So the probability of the, let's see, the probability of getting the car is 2/3 if switch, and then so someone else said that the probability of the car is 1/2 if switch, right? So it could be 2/3 probability if you switch, or 1/3 probability, or 1/2 probability if you switch, because the rationale there was explained that, well, once you know what that one door B has a goat behind it, well, then it's so 50-50, right? Yeah. So does anyone else have any other thoughts or views on this? All right, let's just see a show of hands. Who thinks it's 50-50 to switch after you reveal the one goat? And some pretty tepid hands there. And who thinks it's 2/3? Okay, a little bit more. Some tepid hands, a few kind of fairly confident hands. So okay, yeah. So you think I should go through this, or would you like to think about it? So I should go through it while it's fresh. So sure, okay, great. So so this actually created what this was like posted in like so like a newsletter in like a newspaper, and like a question and answer thing with like, you know, someone who was supposed to be like very smart, and they said that it was the probability in the car if you switched was so 2/3, and this created a lot of controversy. And if you state stuff slightly differently, then you could like there are different ways of seeing the problem. There were a bunch of like statisticians who said that is incorrect. It's not 2/3, but it turns out the answer is that if you switch, the probability of getting the car is 2/3. Okay, so it's not 1/2, and this is kind of confusing. And you know, I hadn't thought about this for a while until I was preparing for this lecture, and my first instinct was that it was that the answer was going to be 1/2. Actually, I'm like, well, once you revealed that one door, now you're a 50-50 chance, and it should be kind of 1/2 of getting the car if you switch. So it didn't really help to switch. Okay, but you know, if you think more carefully about it, the ordering of this sequence is pretty important. At the point when you chose door A, right? When you chose door A, what was the probability that you chose the door so with the car behind it at that point? Yeah, so at the point you chose door A, if I stopped here, the probability that door A has the car, right, that let's say A has the car, then this is so 1/3. All right. And then I get more information. But I didn't know at the point, I didn't know I was going to choose door A. I could have chosen so kind of any of those doors. I'm effectively choosing a door at random, right? So did getting the information actually change the probability that I guessed so correctly? It doesn't change the probability that I initially guessed correctly on the first door. Okay, it changes information about what you know about the other door, but it doesn't change the probability I guessed correctly. And there are always at least two. There are two goats, so Monty Hall can always choose a door that's going to have a goat behind it, right? So you know, if I had slightly changed the problem and said, instead of Monty Hall actually opening the other door, he said, well, I will give you a choice to get both of the other doors. I'm not going to open them, but you can switch to get what's behind doors B and C. Then what's the probability that you're going to get the car if you switch to get doors behind B and C? Yeah. So 2/3, right? There are three doors, right? A, B, and C, and without loss of generality, kind of you either can choose door B, or you say get doors B and C, right? So the probability of, you know, that the car's behind door A is 1/3, and the probability that it's behind B or C, probability of B union C, is so going to be 2/3, right? So what if I changed the order and I said you can have what's behind B and C, or you can choose the non-goat thing behind doors B and C, right? You can look in both and then choose the car if you want the car, right? Well, then 2/3 chance there's a car behind there someplace, and then you can open both doors and check. And so the fact that Monty Hall opened one of the doors to reveal the goat gives you that same process, right? So hopefully it's, you know, a little bit clear that it's behind door, you know, that if you switch, it's actually so beneficial. So another way I saw to look at this is, let's say you have like 100 doors instead of 3 doors, right? And you first pick one door at random, the probability, and there's one car, and so 99 goes, right? You pick one door at random, and then what Monty Hall does, he looks at the other 99 doors and opens 98 of them to reveal goats, and say, now you can switch between the door you have or the door that the door that is left over from amongst the ones you didn't check that had all the goats. Now the probability of switching, you should have 99% chance of getting the car if you switch in this case, right? This is the same issue, but with just kind of, more doors at hand. To make more sense that it's really that first choice was 1/3, and that doesn't change by opening all these other doors. All right. Yeah, okay, so you've got 100 doors, you pick one at random, Monty Hall picks one of the other doors, one of them then reveals a goat. Okay, now, so should you switch? Who thinks you should still switch, and who thinks it's not gonna matter anymore? So still switch, and who thinks it's not gonna help anymore? All right, so the answer is it's still gonna help, but not as much. Right? You've reduced you still had a 1% chance of getting the car on your first door, and on your second door, you have a 1 out of like a 1 out of 99 chance. No, you should have a 2. Yeah. Yeah. So this is a good question. What is the probability you get the goat on the second try? Right? So the first door. All right, so you have the probability of getting the car is 1 out of 100. And then reveal goat. Right, and then there are going to be 98, doors. Okay, and so what should happen is that the probability of getting a car, of switching at your door, of keeping your original door, or getting all the other 98 doors should add up to 1. Okay, and all the other doors. So it should be equal. So you have 0.1 plus 98 doors. So there's 1 door here, and you have 98 doors to choose that are equally likely, times x. This should be equal to 1. Right? So we solved for x. That's the probability of choosing one of those other doors, and so having the goat. Right, so if we solve for this, it should be, this should be 0, 1 here, right? Okay, so now we have 98x equals 1 divided by 0.01. This is equal to 100, right? And so the probability is going to be 100. That's not good, huh? I should subtract here. Okay. Here's what my mistake I made. Okay. This is gonna be 1 minus 0.01. Yeah, so I'm subtracting this guy from both sides. Okay. So 1 minus that's going to be 0.99 equals 98x. And if I solve for x, that's 0.99 divided by 98. Okay, so that's the probability that my other choice, and let's see, is this bigger than 0.01? So barely. Okay, yeah. If it was 0.98 divided by 98, that would be 0.01, so it's slightly bigger. What? Okay, so this is 0.010101. Okay, so I get a slightly improved chance if they open one door, but not a significantly improved chance, but you know, might be, you might as well go with that. It's improved, yeah. Yeah. Okay, so if he opens the door at random and it happens to be a goat, but there was a chance he opened the door and it was a car, and then you're stuck with, you know, goat or a goat, right? So then it shouldn't matter, right? Because there's a chance you didn't get the car when he randomly so selected that door, right? He's not combining the chances of those two cars together, you know, the other two doors together. He's giving you a chance just to switch to another sort of random door, and he's absorbing that one door's chance. So there's a third chance that you fail, that you don't get the car, so no matter what. And then you have the 2/3 probability that he didn't reveal the car, and that is split 50-50, switching or not. So at that point, it's not going to help. Yeah. All right, cool. Okay. So hopefully kind of, so I'm hoping these brain teasers are kind of a little bit, you know, fun than the actual lessons and keep you engaged a little bit. You know, if as a whole you're finding them, this is distracting, I want the hardcore material and, you know, nothing but, you know, then you can let me know and we can not try and do these, but hoping they keep you engaged. So, okay. Great. So today we're going to be talking about a concept called total probability, which we've kind of been using a little bit. We've just kind of slowly unrolling these different ways of thinking about stuff. So I'm going to kind of reveal some different ways to think about probability and the total probability rule will be kind of the centerpiece of tying these things together. All right. But before we do, I want to there was some stuff on independence I didn't quite complete. So I'm going to complete that first before we get to the total probability. So just review of independent events. And we'll talk about independent random variables later, which will be a little bit different. Independent events A and B. And we said there are kind of, you could write this as the probability of A is equal to the probability of A. So conditioned on B being true, right? So the knowledge of B being true does not affect the probability of A. That's a way of interpreting this. And there are kind of some other equivalent expressions which we derive by some simple simple algebra. And these are probability B is equal to probability B given A, right? So I can switch the roles of A and B. It's symmetric between A and B. And we can also say that the probability of A and B being true, the intersection, is probability of A times the probability of B, right? So these were true. Okay, I want to, the one last thing I didn't talk about is there's another view of this we can reach, that this is also equivalent to also that we could write this as the probability of A given B, or let's say the probability of A is equal to the probability of A given the complement of B. Okay, so we're talking about an event B, but what we said, we learned that B was not true. right? Instead, we learned that B was true. How does that affect the probability of A? Well, I want to say it's also equivalent to saying that we learned that B is not true. That also should not affect the probability of A. Maybe this is obvious and intuitive just to say it this way, but I want to formalize these are also independent. This is kind of a shortcut. All right, so you can use these formulas as well. So this is equivalent to probability of B equals probability of B, or I could say B complement given A, or the probability of A intersection B complement is equal to the probability of A times the probability of B complement. Right, or I could even write similar things with A and A complement, or or A complement and B, or with A complement and B complement. That still says the events A and B are independent of each other. So I can use the complements as well. Right, so I'm kind of, one way of thinking about this is that, one way I like to kind of draw a picture here. So it's like a Venn diagram picture. Okay, let's say that this is the whole sample space, and I write the event A as here, okay, as this part of the sample space. And I think of, conceptually, I think of B as being like this, okay? So if B is this part of the sample space, these are kind of orthogonal to each other. I have X and Y kind of coordinates here. If I restrict to B, well, then I have the same proportion of A. A only depends on the X coordinate. Whatever X coordinate I choose, this point is not an A, and this point here is an A, right? It only, for any Y coordinate I get, it only depends on A, right? So if I restrict to B, then I get the same proportion of points are inside of A, restricting to B. And the same is true if I restrict to B, so complement as well, right? I've just kind of taken the total sample space and I've cut out a piece that has the same proportion of A in that piece as I have in the whole. So it makes sense that the complement also has to have that, that sort of property. Having independence between two events does not need to look like this picture, but this is kind of a convenient way to kind of think about intuitively what's going on. You can come up with other events that have the same, the same proportion. Right, I could have events that look like this, which are also independent. Think of B has so if I have, again, this is B and A. If A has 1/4 of the volume inside there, and B has 1/4 of the volume, and then their intersection is 1/16 of the volume, I still have the proportions kind of equal within each of those carved out pieces. So it doesn't need to look like this kind of X and Y coordinate setting, but I think this is useful to think about and kind of intuitively helps explain why this is true. Let's go and derive it just with some formulas, right? So we're going to start with this definition of independence of A and B. So the probability that A and B are true is equal to the probability of A times the probability of B, right? And so I'm gonna kind of use some equalities to change one side at a time. So we're next going to go to that I can rewrite this left-hand side as the probability of A minus B complement. Okay, this is equal to probability of A times probability of B. Okay, so A minus B complement. So this is kind of the trickiest step here. So let me just draw this. Right, so the intersection intersection is just this region in here, right? And so A, if this is if this is all of A, then I want to subtract off the complement of B. So the complement of B, stuff not in B, is everything out here, but also stuff that's not in the intersection. Okay, so I'm subtracting off the green part, but not, but I'm not removing it if it wasn't originally part of A, right? So if it's not originally part of A, I don't subtract it. So all that's left is the purple part in the middle. So these are equivalent to each other. A intersection B is equal to A minus B, so complement. Okay. Once I'm here, I can I can write this out as probability of A minus the probability of A union or A intersection B so complement, right? Again, this is the part in A minus the intersection with B complement. Minus the so that's minus the intersection, right? So that's still going to be the same part, and this is probability of A times probability B. That's the same. Okay. And now I can change the right hand side. So I'll bring this part down again. A intersection B complement. This is equal to, I'm going to replace probability of B by 1 minus probability of B. So complement, right? The subtraction rule. Okay, and now I can, that part on the right there, right? This part, I can take this 1 minus and factor that out, right? 1 times probability of A is probability of A minus probability of A times probability of B. So complement, right? This is going to be equal to, there's going to be a probability of A on both sides, and I'm going to subtract this from both sides. So I'm going to get minus probability of A intersection B complement is going to be probability of A, negative probability of A, probability of B, so complement. Okay, and I can get rid of this minus sign on both sides. Okay, and then this, this is actually the definition of A being independent of B, so complement, right? Let me write this more clearly. Probability of A intersection the event B complement is equal to the probability of A times the probability of B, so complement, right? So if A and B complement are independent of each other, right, which is what I wrote at the bottom, I can go back up and I can get that the probability of A and B are independent of each other, right? So I recover this kind of this definition of B complement versus a B. Okay, so these are kind of equivalent statements. So I can use the independent from the complement or from the event itself. All right. Okay. So just to convince you it's true, for the these are useful rules that we saw earlier, and maybe might be useful to review for your the homeworks you had to do before probably. But at this point, just knowing these rules will be helpful in understanding if things are going to be independent from each other. Okay. Good. So total probability. Okay, so this has to do with when I have a large sample space, right? And I'm going to partition this sample space into some sets, into some regions. Call this region B1, this region B2, B3, and B4. So if I have partition of a set, and for this rule be useful, think of the set as the entire sample space, into B1, B2, up to BK, okay? Then this implies that implies one, that each BI intersection BJ is going to be the empty set. They are so disjoint. Okay, all the sets are disjoint from each other. B1 and B2 don't overlap with each other. There's no overlap between B1 and B2. Okay, and two, if I take the union, right? So let me write it: B1 union B2 union ... union BK. This is equal. I can usually write this as a big union, J equals 1 to K of BJ, right? So this is like writing a big sum, right? If you use the sum notation, you have a big union, you kind of can add up all the sets. This should be equal to 1, or in this case, should be equal to the total sample space, the total set. So if I have partition, every element from the original set is in one of the subsets. That means if I take the union of everything, I recover it, and there's no overlap. Okay, so we're thinking about, what if we divide a set up into these disjoint pieces, and the disjoint pieces cover the whole set. Okay. Okay, so now let's say we have a partition B1 through B2 up through BK of the total sample space. Okay, then I can say that the probability of an event A, okay, this is another event, and I can think of each of the BJs as events, okay? Then this is going to be equal to the probability of A given B1 times the probability of B1 plus the probability of A given B2 times the probability of B2 plus ... probability of A given BK times the probability of BK. Okay, so or more compactly written, J equals 1 up to K, the sum of the probability of A given BJ times the probability of BJ. Okay, so I can break it down into the I can break down the space into these these components, and I can get the total probability of A by adding just the contributions of the components, right? If they were not a partition and they overlapped, I'd have to like subtract out what the overlap was. So the partition here is kind of important for this to work. Okay, let's look back at this picture, and then we'll go through some like not picture examples, but some like real examples of this, right? So we have this space, B1, B2, B3, and B4. And then I have an event A, right? So I have this overall event here that might overlap some of these partitions. It doesn't need to overlap all of them, right? I might also have, this is B5. It does not overlap B5, okay? So to get the total probability of A, I can say, well, I can think of there being some underlying process where I first pick a one of the pieces, like B3 at random, proportional to its probability, and then I look at the probability that it's in, so B3, right? So I can look at, so I pick B3 at random, and then I look at the probability of A restricted to B3. So there's this two-step process. I choose one of the things, and then I look at the probability given in there. I multiply these together, and I add all these up. Okay, so this is kind of a way to kind of get the total probability of, so some sort of event A. Okay, so for instance, an important way we've seen this already is if A is the entire space, right? If A is equal, so if A is equal to the whole sample space, well, then this is, and then we know that that the probability of the whole sample space is equal to 1, right? This is by definition. So then that's just saying that this sum, J equals 1 to K, of the probability of the entire sample space given B times the probability of Bj, right? Well, we know because it's the whole sample space, this term has to be 1, right? The Bj must be a subset of the whole sample space. So the probability we're in the whole sample space restricted to some Bj is 1, okay? So that means that this is equivalent to J equals K probability of Bj, right? And those must add up to 1, right? Those are a partition. If I pick one of them, like if there are 3 doors from the Monty Hall problem, I must pick one of the 3 doors. Or if there are 100 doors, I must pick one of the 100 doors. So maybe the probability wasn't uniform, but it has to add up to 1. So we've seen this is the definition of probability. All right. Okay. Great. Okay. So let's go through. Oh, and I'll say one kind of pretty simple other way of seeing this is that the probability of A given B times the probability of B plus the probability of A given B so complement times the probability of B so complement, right? So if I have two ways B can go, the only way is to get A is if B is true, well then it's the probability B is true times the probability I get A given that B was true, or B was not true. So I add the chances that B was not true and then the probability of A given that B was not true. These should add up. These are disjoint kind of things that can happen because one is conditioned on B being true, one's conditioned on B being not true, and those both can happen in the overall AB kind of sample space, you know, that's divided by B or not B. Yeah. Yes. And B is always disjoint from B complement, right? Something's either true or not true. There's no like maybe a yes, right? If it's either true or it's not true or maybe. That would be the complement of true if maybe was an option. Yeah.
You could also reach this by using the set equality of the set A is equal to the set A union B, A intersect B union A intersect B complement.
All right, let me see if I can write this down. So, the set rule. So so can you say this again? So A intersect B?
So A is equal to A intersect B union A intersect B complement.
A intersect B, so complement. Yeah, okay, great, yeah. So this is also so set rule, and so we can write A as these union of the things, and union means that if they're disjoint, we can add them, right? If they're not disjoint, maybe I should also subtract off probability of, I should subtract off A intersection of B intersection B, so complement, so I don't overcount, right? If I use inclusion exclusion rule, but that last term, B intersection B complement, they're disjoint, so this is the empty set, right? So that this term whole I can ignore. Okay, if that helps for thinking from a set perspective, then great. Okay, so let's go through an example problem. And we've seen problems like this before, but we have two urns. Okay, these are little smaller urns. Okay, so this guy here is between two urns. Okay, so two urns. Okay, and the first urn has 4 black balls, and it's going to have 3 of these red balls, right? And then the second urn is going to have 2 black balls and 2 red balls. Okay, and then I'm going to step 1, select an urn, and then 2, select a ball from urn, right? So this is, again, this 2-step process. We've analyzed this before, and we could solve this by we had looked at this before by saying, okay, this is urn 1 and this is urn 2, right? So there's a 1/2 probability of being in urn 1 and a 1/2 probability in being in urn 2. Okay, and then given here, I can either select a red ball, or a black ball. Okay, and the probability of selecting a red ball in urn 1 was going to be 3/7, and that means a black ball was 4/7, and given a red ball in urn 2 is 1/2 and 1/2 here, right? So then we can write down the probability of selecting urn 1 and then a red ball is the product of these. It's going to be 1/2 times 3/7. This is 3/14. This is the probability of getting urn 1 and a red ball from urn 1. We can also say this is 1/2 times 4/7. It's going to be 2/7. That's probably getting a black ball from urn 1. Probability of getting a red ball from urn 2 is 1/2 times 1/2 equals 1/4. And getting a black ball from urn 2 is 1/2 times 1/2 times is equal to 1/4, right? So this was the probability tree we talked about and you did for your homework. Okay, so now we want to say what's the probability of a red ball, but I don't care which urn. I want to use the total probability here, and the B event is going to be the choice of the urn. Okay, so this event, kind of think of A equals a red ball and B equals urn 1, right? Or maybe urn 1 is B1 and urn 2 is B2, but we can do B is urn 1 and urn 2 is the complement of B. Okay, so I can write down that the probability of the red ball is going to be the probability of red given urn 1 times the probability of earn 1 plus probability of red given earn 2 times the probability of earn 2. Okay. Well, I've actually calculated these already. This probability is actually this product right here. I picked earn 1. That's the 1/2. And then I took a red ball given I was in earn 1. That's the 3/7. So this is 3/14 plus, and then I've calculated this other one. Here, this is equal to this probability. This is probability I selected earn 2 times the probability I got a red ball given I was in earn 2. Okay, and this is equal to 1/4. And so the answer is 3/14 plus 1/4. That's a probability I got a red ball. That's going to be what is it? 13/28. That's right. Okay. Great. So that's how you get the total probability you get the red ball is you add up these different routes, right? Think of there are these different routes of going here or going here. It doesn't matter the route I took, I got a red ball in either case. So those are the two ways of like getting the red ball. All right. Are there any questions on Zoom I'm missing? Or you? All right. Great. Okay. Okay. I want to talk about. I want to finish before we do the quiz with another kind of way of thinking about probability. I think just to kind of round out some, give a different perspective to the way we've been thinking about it a little bit. So if we have two events, and so this will tie into total probability just a bit, okay? A and B, right? We've been saying, well, there are a bunch of ways we've been thinking about this. One is that we can have kind of event A and event B. Okay, and there are these kind of two different events we could think about, and they could be both happen. It could be neither of them happen. The Venn diagram. Another way to think about this would be a truth table. We could have A and B, and so we could put a 1 if A is true, and a 0 if it's not true, and a 1 if B is true, and a 0 if it's not true. Okay, and there are only 4 possible outcomes, right? Either A is true and B is true, or A is, which is the first row, the second row is A is true, but B is not true. Okay. And then I said, I said when we defined probability, right? So probability was a function. It was this function P that went from these subsets to kind of a value between 0 and 1, right? So this went from sometimes we use this power set to two values between 0 and 1, and it had these two properties that for any subset of all the of the total sample space here, it had to be between 0 and 1, and if you added them up, they disjoint all the disjoint things, then they would equal to 1. And so we can see this here as think of a function P, and we can assign, say, some values. The probability A and B is true. Maybe I'll match it with the area a little bit more. It's like might be 0.1. Probably A is true and B is not true might be 0.2. That B is true, right? But A is not true might be 0.3. And that neither is true is 0.4, right? So if we have A is true and B is not true, 0.2, that is A is true and B is not true. If you look at the Venn diagram, I'm basically think of the regions where I'm not allowed to cross over a line, assuming each of the kind of the different ways I could look at this subset is, they're kind of so contiguous, right? That line is there. This line of A and B being true, that's in here, right? And this maps to this sort of probability, okay? A and B is true, but not A. That's this region over here. Okay, and then everything not shaded, that's 0.0, so 0.4. So this is kind of another way of thinking about it. And if I did this correctly, 0.1 plus 0.2 plus 0.3 plus 0.4, these are a disjoint, so partition, and they add up to 1, right? This is 1.0. So these probabilities, these are the only things that can happen. Either A happens or it doesn't. B happens or it doesn't, right? So these are the only 4 possible outcomes. And so the sum of the probabilities has to add up to 1. Okay. So kind of this is a convenient way to think about. Now it doesn't need to be like, I don't need to have like area on top of those shaded. It could be any function, right? So I could have that even though I drew the Venn diagram that way, A and B being true might be 0.9 probability of happening, right? There could be some other functions, but let's not worry about that for now. Okay, another way of thinking about this is a probability table where I could think of A as being true or false, and B as being true or false, being the event A happens or it does not happen. Actually, it's a little smaller. Okay. And so now I can write the probabilities in here as well. And we previewed this in one of the examples. A and B both being true is 0.1. A true, but B false. This is 0.2. B true, but A false is 0.3. And this is 0.4, right? So these align with these same colors as before. So this is another way of thinking about it. This is, the A and B true is also the set A intersection B, right? These are all equivalent ways of thinking about it. And now what I haven't written down is, say, the probability that A is true yet. Well, the probability A is true is I can write down here in the margin, I add up those two conditions. Condition on B being true, what's the probability A is true, right? So I get a 0.1, that means they both have to be true. And the probability that A is false is 0.7. Can also add up the probability B is true is 0.4. And the probability B is false is 0.6, right? And if I add up these things on the margin, 0.3 and 0.4, down here, this should add up to 1, and this should add up to 1. Okay, so these are kind of different perspectives of ways of thinking about probability and events at this point. Again, I think we've used a number of these in the examples, but I just wanted to kind of clarify and write all these things down. All right, any questions about this? All right. How about we stop here? The quiz will open in just 1 minute. And then, so if you're gonna stay here for the quiz, it'll be quiet in 5 minutes. If you're not gonna stay for the quiz, please kind of pack yourself up over the next 5 minutes or so. Again, once you start, you'll have 10 minutes. If you want to pick up or printed homework 3 is out. I've got a bunch of copies up front here.